Okay, hello and welcome everyone to this second YMSC lunchtime webinar. My name is Mohamed Elzeadani and I'm the chair of the Second Young Members Subcommittee. And I'm delighted to have with us today four speakers, Professor Eleni, Dr. Gregory Duthé, Lidiya Kennedy, and Dr. Konstantinos Vlachas, who's going to speak to us on leveraging physics and data for advanced modeling and monitoring of wind energy infrastructure. Just a few housekeeping rules before we begin. Please keep your cameras off and also your microphones on mute for the duration of the presentation. And also please note there will be a Q&A session towards the end of the presentation. But in the meantime, if you have any questions, then feel free to type them in the chat and we'll get to those towards the end. And also please note that this seminar is being recorded and will be uploaded to our second YouTube channel. So by joining this call today, you consent that any comments or information you share will be made public. Okay, and for our speakers, we have quite the list of speakers with us today. Professor Eleni, she's quite the superstar in this field. She's the chair of structural mechanics and monitoring at ETH Zurich and president of the European Academy of Wind Energy. Her research lies at the intersection of structural dynamics, digital twinning, and physics-informed machine learning for infrastructure systems. Dr. Gregory Duthé is a postdoctoral researcher at ETH Zurich and a member of the Swiss National Science Foundation project Mystery, focusing on digital twin frameworks for wind farms, integrating hybrid models and data analytics to enhance operational resilience and optimization. Lidiya Kennedy is a doctoral researcher at ETH Zurich and a member of the doctoral network program in TeleWind, working on graph-based reinforcement learning for adaptive wind farm control. And last but not least, Dr. Konstantinos Vlachas, who's a senior researcher at ETH Zurich and a member of the Horizon RIA Action Turing, specializing in physics-enhanced machine learning and reduced order modeling for dynamical systems with a focus on turbulence and structural response prediction. So very much looking forward to the presentations, and I hand over to Professor Chatzi.
Okay, thank you very much for the kind introduction. If you can see the screen now.
Yes, we can see your slide, yes.
Great. So thank you very much for this invitation. I was saying that I very much like the format where you invite the different group members to offer some inputs. And for this, I would like to give an intro that is a bit broader than just wind energy structures. It's about our vision on monitoring and modeling different types of structures and infrastructure systems. And maybe here to ask you if you can see the entire screen or the presentation mode, because now I don't know which one is shared.
We can see the slides, just the presentation.
Good. Okay, great. So let me give you this kind of rough overview without taking too much time, which essentially lies in our view of infrastructures or large safety critical systems as cyber physical entities, which implies entities that integrate within them the aspects of sensing, computation, control, and networking, meaning that we do not just view the physical assets as sensitive structures that are exposed to threats from the environment, but we rather try to elevate these in a sort of hybrid representation, a sort of digital representation that is, however, active in that it offers a two-way communication between the physical asset and the processes and actions that we can, let's say, take upon this asset. So in order to make this kind of link, we rely on data, the availability of data that can be available in different types of forms. And today we know that such data can be extracted with various types of sensing technologies and at various scales, even from large-scale infrastructure systems, especially wind energy structures. And they can be extracted to offer information not only on the response of the system, which is typically what we try to seek through structural monitoring solutions of various types, but also on the loads that are acting upon this system and the environment within which it operates, which of course could be an environment that degrades slowly, something that is obvious with climatic actions, but also could be an environment that rapidly changes in the faces of different types of extremes that could actually jeopardize the health and safety of these systems. And gathering information throughout these operational cycles is very important for us, not only for effectuating different types of triggers for their repair and reaction, but also for modeling how these systems evolve and how we can actually improve them. And in the chair of structural mechanics and monitoring, we actually are in the, I guess, lucky position to have experience with different use cases, a bit beyond the domain of wind. Actually, wind is one of our perhaps biggest or largest domain of activities at this point in time. We even own a wind turbine structure not too far away from our lab, which we use as a living lab where we experiment with different types of sensing technologies and algorithms for structural monitoring. But we're also lucky enough to have or gather experience from other systems, including railway monitoring, more conventional civil infrastructure, and even industrial assets. I say this because the methods that we use are actually inspired from problems and issues that are met throughout these systems. And it's interesting to note that some of the sensing technologies are also applicable more broadly. But maybe to frame the approach that we follow, it's interesting to say what we can do with data alone. And wind energy infrastructure systems are good in this respect because they are data rich. So in fact, we are in the position to gather SCADA, as we call it, information from numerous such, from every wind turbine, actually within a fleet, which is usually averaged information over 10-minute interval, but still rather important information about the operational landscape within a farm. And in previous work, we have actually exploited this data-rich landscape to model, let's say, phenomena that are quite intricate within wind farm operation, which is, for example, the phenomenon of wakes, which you see depicted in this by now rather, let's say, infamous picture. You see the effect of front-facing turbines on those that are in the shadow of these front row turbines, which of course creates these wake effects that are not only affecting the power production, but also the fatigue. And what we did by using this data-rich landscape was to create data-driven models. At the time, this was created by Harry Milonas when graph neural networks were not yet a thing. And he managed to create a data-driven framework that somehow predicts the landscape of wind, given mean wind film conditions within the farm, and also predicts the effect of these wakes that you see here. Excuse me, it was a bit slow, so let me go back. And let me try to start the video where you see here the evolution of what we call the wake deficit, which explains how these turbines are actually affected by the influence of wind and their positioning within the farm just by using data-driven information. But what we claim within the group is that actually this kind of approach where we try to learn from data cannot be considered as enough. In the previous example, for instance, we can only learn as far as what we observe. And so the minute you want to move away from these kind of diagnostic twins or models that they can actually predict for the range of influences that they have observed, and you want to go a step further into prediction and forecasting, eventually for tasks that have to do with digital twinning, that have to do with the awareness of the twins, their capacity to extrapolate beyond their training region, we have to bring our physics intuition into the loop. And so when we say that data is not enough, we're actually referring to the process of informing the learning of these data-driven models or machine learning models through the inclusion of physics biases. We tried to frame this in a paper that recently came out for what we call hybrid digital twins. And we did this in cooperation actually with industry-based stakeholders in Singapore, where they as well try to put forth this vision for cognitive twins, meaning twins that are not just reactive and diagnosing a situation of a system as this, but rather go a step further into prediction. And in our group, this is effectively what we do, particularly for wind energy systems, which are actually operating beyond the linear time invariant behavior. They're operating under continuously varying environmental and operational loads that are distributed and not well understood. They are not necessarily measured precisely. And we try to see this kind of logic of learning from these systems by exploiting physics into the loop and acknowledging that this physics is not always easy actually to fuse with data. So there are particular actions that we have to take that you will hear as part of this talk. For example, reduction of the quite detailed engineering models so that we can blend physics and data in one landscape, in a hybrid landscape that can be used for different types of actions that include decision support for operation and maintenance, include actions for control, and that we can actually imagine to implement in real time. I saw you here such an application that was quite paramount for us. It comes from a previous PhD student of our group, Dr. Silvia Vettori, who was part of a larger European project, where the task was to try and deliver a digital twin of an actual operating blade. This was actually set up in controlled conditions in the lab, and you see here the blade, which was instrumented over its length with different types of vibration-based sensors, accelerometers and strain gauges, or tilt meters in this case. And what Silvia did was to implement the logic that I described and that lies at the core of our strategy, which is to build a reduced order model based on physics, finite elements in this case, and substructuring methods for this blade, and to fuse it with the data that was drawn in real time at high sampling from the accelerometer and strain gauges, and then eventually through and blend them through a Bayesian logic of a Kalman filter, which operates in real time. Now, what this outputs for you is actually the full field response of this structural system, the blade in this case. You can actually imagine to plot quantities of interest that include strain and stress throughout the surface of the system as it operates, or as it's being loaded in this case. And our colleagues at Siemens Industry Software, where Silvia was based and currently still is based at, developed this sort of augmented reality platform that would deliver the output in a form that is easy for the engineers to interpret, not only for the obvious task, which is diagnostics, something going wrong with the system, but more importantly, once you have such a calibrated model, for forecasting tasks. So what happens when you have new and increased loads, for example, and how do we assess the reliability and robustness of the system under these loads? This is actually what is underpinning our approach, and there are two spin-offs that actually came from our group that are trying to implement these concepts with RTD implementing them in wind energy structures. There's one more thing I want to add, which probably will become apparent in what is presented next, which is what do you do with complex systems? And here our approach is to explain that it is not always enough to claim that we have the amount of physics at hand that is sufficient to describe the system. Rather, we try to approach the problem as a two-axis problem where physics, on the one hand, represents how much knowledge or confidence we have in the first principles that underlie the problem, and then the data axis shows how many data or how much data is available. And there's a different scaling that you can do. And in a recent paper, we explain how different methods can be used in what we call this physics enhanced spectrum, can be used to fuse physics and data at different weights. A number of these methods exist, and as part of the group, we have been developing different subcategories of schemes that you can imagine can be used to fuse dynamics equations, for the most part, within flow of data that is usually vibration-based data, and that can be characterized with different terms depending on how you imagine to fuse the physics into the problem at hand. So I invite you to also look into our further works. I think this is a good introduction with respect to what you will see described next from the members of the group. Because I don't want to take much time, I'll just take you to the overall vision that we have, which is to exploit our engineering intuition and knowledge, which is something that we have always been using for what we engineers call design, which is the forward simulation, and now take it into consideration for what we would refer to as the inverse problem, the problem where observations, monitoring data, inspection data become valuable, and where even the knowledge of the expert can be exploited to guide operation, maintenance, and overall management of safety critical assets, and especially wind energy structures. So I stopped with the framing, and I rather give it over to the members of the group to show you a bit more on how, for us, this is achieved. I'm not sure who goes first, but you can help me based on your program.
I think in the list I was going first, but
correct me if I'm wrong.
All right. So hi everyone, my name is Gregory. I'm a postdoc now in the group working on the wind energy in general, but mainly we're using geometric deep learning. And the work I'll be presenting here is some of the work I did during my PhD, which is about efficiently modeling wake-induced loads in wind farms using graph neural network-based surrogates. So what is the big problem? Well, Eleni already briefly mentioned it. Well, it's these wake effects. So front row turbines cause increased turbulence on the back row turbines, and obviously this comes with a cost. These back row turbines see reduced power, but something even more important and more difficult to model is the increase in fatigue that these back row turbines experience. And how would one typically model this? It's quite a computationally intensive process where you start with multiple air elastic models. Typically in the wind turbine industry, we use OpenFast, or Hawk2 is another air elastic modeling tool. And then we couple these air elastic models together using a wake model. And so each air elastic model will compute the dynamic response of the turbine, and then through the wake model, we have multiple of these air elastic models coupled together. This is a computationally expensive process. And even if you use the simplest wake models, and from the air elastic models, we compute our damage equivalent loads, which is the quantities of interest. And even if we were to use the most simple wake model, such as something very just using Gaussians, like what is used in Flores, or something much, much more complex like LES, well, all of this is really expensive. And so computing these damage equivalent loads using coupled air elastic models is very costly. And so we want to find an accelerated way to do this. And to do so, we use graph neural networks as an efficient surrogate model. So how does this GNN work? Well, we start by taking our wind farm. Our turbines become the nodes of our graph. Then from once we have the nodes, we then need to connect them together using some kind of connectivity scheme. In this case, often we use something like Delaunay triangulation to avoid having disconnected communities, but we could also go, for instance, for a fully connected scheme. We then take some geometric properties that we append as edge features. These become the edge features of our graph. And we have our global inflow condition, which is a graph level attribute as it affects all the turbines in the graph. We then take this initially empty node graph with initially empty nodes and the edge features, as well as the global features, feed them into our encode, process, decode GNN, after which we get updated node features, which are the quantities of interest, in this case, the damage equivalent loads for multiple components at each of the turbines. And I briefly mentioned this encode, process, decode structure. This is quite typical in GNN applications for physics because it allows just for much more expressivity. The idea is we take the initial features and encode them or project them into a high dimensional latent space using simple MLPs. The processor, this is where the key step of the GNN happens. It's where we have this message passing, where we transmit information from one node to the next. And briefly, just how this works is, well, we first compute messages for each edge, which is connected by 2 nodes. And then we aggregate and update the nodes. And by doing this iteratively, we can propagate information in our graph. After we've done a sufficient amount of processing steps, we decode back into the physical space using, again, MLPs. Now, the training strategy we use in this work is to first create a very generalist GNN by pre-training it on thousands of random layouts that we generate using a cheap simulation tool called PyWake. The idea here is with this generalist GNN, we want to learn the fundamental physics of the problem. And then what we can do is, if we have access to higher fidelity data, we can adapt and fine-tune this generalist GNN to this higher fidelity data, or for a given layout, for instance, using efficient fine-tuning. In this case, we use low-rank adaptation. And in this case, we get a specialized model where the training has been bootstrapped, and so it's very efficient as well. Just some base results for the generalist model. You see that we can capture quite accurately the behavior of the damage equivalent loads, even if they are quite nonlinear with regards to wind speed and with regard to position in the farm. For instance, the front row turbine, in this case, the orange one, sees much lower damage equivalent loads for the different components with regard to the back row turbine. And our GNN accurately captures this. We can then also look at this from a polar plot perspective, where you can see that for two turbines on opposite sides of the farm, we have almost mirror-like behavior from one of the turbines to the other. And this is quite difficult to capture, but our GNN does as well. Next, just some results on the fine-tuning example. So with only 100 samples of a higher fidelity data for a given farm, this is the an existing farm layouts. And you can see that, again, our model is able to capture this well, even despite it's being different turbine to the training turbine, because it's a much larger turbine model in this case. And we can adapt using only 100 samples. This is really not a lot. The last extension that I briefly want to mention in this work is going in the direction of uncertainty estimation. So we don't want to completely change the model, and we would like to get some estimates of how the model is behaving with regards to uncertainty. So what we use is conformer predictors, where we basically reserve some calibration data to determine guaranteed prediction intervals without strong assumptions on the model. And so what we get from this, again, this is the setup that we had before, where we get point-wise output for each variable. But now we have this calibration data, and we use that to conformalize our GNN, and we can get per turbine prediction intervals for each of our variables. And just as a quick example here, you can see for instance, the dependence on turbulence intensity. As one would expect, the higher turbulence intensity we have, the more uncertainty we get, and this is captured properly by our model. So just to summarize very briefly this work, well, graph neural networks can serve as efficient surrogate models for predicting wake-induced fatigue. The models that we propose are very, very fast. We get a 5 order of magnitude speed up over coupled aeroelastic models. They're flexible, as they can handle any kind of layout, any kind of inflow. We've shown that we can also transfer them, so we can fine-tune for a given higher fidelity for different turbines, for instance. And we've shown that we can also conformalize them, which gives us access to a form of uncertainty quantification. And because of how fast they are, we can then use them for, I would say, difficult optimization scenarios, for instance, load-aware wake steering. And I'll stop here because I think Lidiya will then touch up on a bit of this, as she'll be building on some of the work that I did. And this here are the references the work that I've shown here. All right, with that, I think my time is up, and I can pass it on to Lidiya.
Hi, are you able to see my screen?
Yes,
we can see the screen.
Yeah, cool. So I'm Lidiya. I'm a first-year PhD student at Eleni's chair, and I'm also part of a doctoral network called Interlivent. I'll be giving a brief overview of what I am currently trying to build as part of my project, which would be a farm level optimization for wind farm control and maintenance decision support. So from what Eleni and Greg had already explained, we all now understood these are complex aging infrastructures that are subjected to various physical processes happening at different scales. And this is often not great for the turbine. So in the last few decades of research, there has been increased attempt to reduce the levelized cost of energy, which was driven by scaling up the size of the turbines. But unfortunately, we have reached a limit in scaling up the size of these turbines. So then came the question of efficiency versus scale. So it looks like we could also reduce the levelized cost of energy by making the operations and maintenance much more efficient. But this comes with a lot of challenges. We need to understand the interactions between the entire at an entire farm scale, which is very hard to model, as Greg explained. And the topology becomes much more important, that we need models and computational frameworks that can work across different topologies and different sizes of farms. So this is my main research, where I want to build a computation framework for more generalized support for maintenance decisions. So there are three main research questions that need to be answered to build this computation framework. One is, what is a good model that can from which we can accurately infer what is happening at farm level, and also it is fast enough that we can make inferences for the reinforcement learning agent to make or suggest actions or policies. And what is a good generalizable surrogate model for this? So this is what Greg has already explained, and I'm building upon what he has done for farm level modeling. And how can we best make use of the expert knowledge or domain knowledge that has been accumulated over years to make the reinforcement learning agents make better policies or decisions, or suggest better policies or decisions? So this is the entire framework I'm trying to build. This looks a bit complicated at once, but I will walk through one by one. So first, we need to understand the turbine level physics, what is happening at the turbine level. So we have this aeroelastic models using OpenFast, where we sample different inflow conditions and understand the response of the turbine. And from the load histories, we can understand what is the load on each turbine. And such generated data set is used to train a surrogate normal multi-layer perceptrons to give quantities of interest for, in our case, it is power, thrust coefficient, and damage equivalent loads at different components, where currently we are focusing at blade flap-wise, edge-wise, tower bottom side-to-side, tower bottom fore-aft, and also tower top yaw. So this is how the inflow conditions were sampled. It is based on some literature, and you can see we could simulate around 65,000 different cases, and the surrogate model was full predicting load and power was built based on this. And the next main part of the framework is to understand the complex wake effect across the farm. So we generated different layouts of wind farms, and for different inflow conditions and actions, which would be in our case yaw and pitch angles, what would be the local inflow and local wind speed and turbulence intensity, and based on this turbulence intensity, what would be the power and thrust coefficient, damage equivalent loads at different components. So now we have a model that would give us the wake affected power and damage equivalent loads across different farms, different layouts, and different sizes of farms. Then this generated data set is used to train the graph neural network, which is similar to what Greg did, where nodes represent turbines and edges represent the spatial attributes. And the input features are encoded to a higher dimensional latent space, where a sequence of graph convolutions aggregate and propagate information across the graph to understand the turbine level interactions. And this is then decoded to the physical space. These are some example results from GNN for 3.4 IEA 10 megawatt, 3.4 megawatt turbine, IEA turbine. And you can see the downstream turbine experiences higher loads as compared to the upstream ones. And the results are pretty much good in comparison with the results to Piwik. So now we have a forward model from which we can understand what would be the consequences of different actions, such as yaw and pitch angles on the power and load on the turbines. We can use this as a base for building a simulation environment for the reinforcement learning agent, which could give us policies or actions for controlling the farm. So for the control actions are sampled, as I already mentioned, and the consequences of these control actions can be estimated using graph neural networks. And using Palmgren-Minor rule, we can calculate the damage accumulated over 10-minute intervals, and this will form the core of the observation space, which is embedded to a graph. And the cost and profit of these at each time step can be computed using a dense or sparse model, where dense cost means that the replacement cost, or if a turbine is broken down, it is spread across the entire operating time lifetime of the turbine, whereas sparse cost is like pay per breakdown logic, where cost is incurred when only a component breaks down or a component is replaced. So the idea is to further develop the current framework we have, where we have a single agent that infers actions across the entire farm. But the later idea is to have a graph-based architecture for this, where we have multi-agent architecture. And here, for this, we again use graph neural networks, where the observation space and the state space form the input. And similarly, as we did before, a sequence of graph convolution would transmit information across the graph, and from which we can infer policy head, that is continuous yaw or pitch action, and also the cumulative reward. These are some results from Liljegrund wind farm. You can see different yaw angle versus wind direction results we have, but the plot assumes that the damage state is equal for all the components for all the turbines. But informed agent means the agent is aware of in calculating the reward, we take into account losses due to maintenance and degradation, and also we take into account the power production. Informed agent policy remains unchanged under different damage states. And also these are some of the training results of the reinforcement learning agent. And finally, the idea is to extend this to whether from the damage equivalent loads that is calculated over 6 months, whether we can make some quality health indicators about the health of different components at the farm level, and suggest maintenance actions. And since we cannot fully observe the state of the farm and different components, we would like to cast this as a POM-DP problem, where we assume partial observability. And that's it. And the main objective of also the framework is to understand the best way to encode expert knowledge into the framework. This could be in the form of we collect information regarding, for different scenarios, what would be the actions experts or people in the domain would take under these circumstances, or having some limits in terms of logical expressions that would limit certain actions from being taken under certain conditions, or to have different rewards, were intermediate rewards and penalty functions that guide the agent towards some desired behavior. And that's it. And I will give the floor to Kostas now. Thank you very much.
Thanks, Lidiya. I will also share my screen, change a bit the gear. And I'm going to, I'm Konstantinos Vlachas, Kostas for short, a researcher with Professor Chatzi at IBK. And I'm going to focus on what we, let's say, code here as adaptive twinning for the purpose of optimizing downstream tasks such as structural health monitoring, operational maintenance, and so on. And I know that twinning is a keyword for most of us, but what we would like to emphasize here is this virtual representation I have on the right, the virtual representation of a physical system. The two communicate, of course, through the use of sensing data and information. And there is also this modeling part that makes sure that this virtual component, this twin, hybrid twin nowadays, because we also use the observational data, this modeling part makes sure that this is an accurate representation of reality that can be used for control, decision making, and so on. Now, to assemble these twin objects, twin entities, I'm going to present, or I'm going to rely on three components. The first one is termed reduced order modeling, but because we would like this to be as generic as possible to address variability, parametric dependencies, nonlinear phenomena, or even damage, we would have to make it local. This means that we are going to derive these reduced order models for local portions of our operational domain. And in between, we are going to interpolate, but we would require that these reduced order models are reliable under variability, as I explained, and of course, very fast to evaluate, very efficient, so we can do real-time control or real-time decision making. On top of that, I'm going to use generative learning and specifically conditional variational autoencoders, because variability is not well known beforehand, and in reality, the idea is to generate these reduced order models from sensing data, so to be able to obtain a modeling of your real system conditioned on sensing data, and at the same time obtain not only response predictions, but also error bounds. So this practical generation process aims to give you a model that will give you a response prediction, but also error bounds on that, so you can increase your trust on it. And finally, I'm going to show an ongoing work. We have a preprint that we are optimizing, but the idea is utility-driven selection. This implies that in reality, in a continuous manner, you don't always know which model to use from a pool of potential candidate models you might have, and every decision you make should be optimized with respect to what model is available. So we are going to, in real time, judge and evaluate what value every model that we have available brings for the downstream task, and show a framework that gives you the optimal model at any given time. So let me start by the local reduced order modeling part. This is an assembly that is based of two different components. On the first, we have physics-based reduced order models. This is a collaboration or a combination, if I may, of purely projection-based techniques, so purely equation-based and physics-based techniques, coupled with an additional projectional level. So we are trying to relate local dynamics of reduced order models, of models that we derive for local regions of our domain, with what happened globally and we are doing this to obtain a reduced parametric representation of the model. This X implies a reduced representation of the model. This is the idea here. And as you can see the schematic, the idea is that you have the blue dots, local models, that you have pre-trained, pre-derived, offline, and in between, for any parameters that happen in reality and lie in between your pre-trained regions, you are going to need to interpolate. In order to interpolate, we use conditional variation autoencoders. The idea is here to use a machine learning scheme to be able to infer, to generate models conditioned on sensing data. So W is the sensing data, and essentially this variation autoencoder, it learns a space, what we call here the space of models. It learns a space where you can interpolate in between this space instead of the original parameter domain. So you can interpolate this and you can obtain a reduced order model that is an interpolated quantity of known models, but it is conditioned on the sensing data that you can record in real time. This is the idea. So interpolation happens on the inferred latent space of the VAE, on the space of models as we code it here. And on top of that, because the VAE has a probabilistic nature, it essentially learns a distribution of models. You can derive not a single realization of this interpolation result, but an ensemble, a family, a distribution of this interpolated result. And this implies that you can have multiple evaluations of your response and generate error bounds. This is the main idea behind this framework. And you can see, yes, we have benchmarked this in a structural frame for comparing our results against state-of-the-art approaches. And you can see here, this is just a snapshot of the different behaviors this model can capture. This is a hysteretic joint. The frame has hysteretic joints all over, and the model can capture at once different hysteretic behaviors and different time histories. And on the large scale, you can see here, this is a video of a wind turbine tower, of a wind turbine mast suffering extreme excitation, or extreme plasticity, under ground motion excitation. I need to go back to the slide so the video can start at the same time. And on the right, you can see how precise, how accurate can the reduced order model capture the stresses in this case, even in this extreme instance of plasticity. And this is the note here that we can do this in 60 seconds, whereas the original full order simulation takes 10,000 seconds to evaluate. And you can see the fidelity, both in local, capturing local stress intensity, and in the global picture of the results. So this is the idea, to be reliable and fast. This is the concept. And we have also exemplified this reduced order modeling component in local regions, very localized components, as this track here. It has a kingpin. This kingpin is the component that couples the two parts of the track and exhibits all accelerations, braking, all vibration phenomena. And you can see again how accurate the reduced order model is, in 25 times faster than the original finite element modeling simulation. Now, we have also demonstrated here this in an inverse problem of crack detection. This is an aerospace panel, and you will see here the middle is a sequential filter powered by ROMs. So in the core of the filter, you have ROMs, and it will almost immediately identify the region of the crack. This is a crack here, and after a while, it will also capture the exact crack. I think you caught it, almost immediately identifies the region. So the population is currently in the region of the crack. And after a while, by matching the incoming data through a filter with the ROM simulator, a parametric ROM simulator, it can give you the exact crack that this panel has in terms of damage. So this is the idea, coupling through a filter paradigm, the incoming measurements with a fast forward simulator, and by a proper objective function, identifying the damage, the crack in this case, and so on. Now, okay, let me get to the last portion of the talk, the one that talks about this utility-driven engineering support I mentioned. The concept here is that, as you see, we have a continuous monitoring. So this happens again and again and again and again in a continuous manner. And the goal is, on the other end, to obtain the optimal model at any given time. Why the optimal? Because it might be that you have, first of all, parametric models. So we strive for our models to be as parametric as possible, as generic as possible, to be able to capture different phenomena, nonlinearities, damage, and so on. But at the same time, you might have costly models that are very accurate or very fast models that are not that accurate. And the goal is to obtain the optimal model at any given time. And we do this by solving a utility maximization problem. So we try to balance the value every model brings by being accurate and the value it brings by being efficient. This is the idea. And you have these two competing attributes that you need to balance via Bayesian decision theory. And you can see, of course, in the terms of accuracy, overestimation or underestimation of certain response indexes can be penalized differently. This is the idea. And this leads to a continuous evaluation of the utility, a continuous evaluation of how useful, what value does this every model brings to the table. And of course, for every single instance, you can get the optimal model to obtain the optimal response and the respective error bounds. And you can see that even in the worst case scenario on the right, where you have the actual response, the red one, sorry, the approximated response, the red one, being not that accurate compared to the black one, due to noise, perturbation, and so on, the error bounds that are properly, suitably computed, they can capture the actual response and still give you an idea of what is happening, even though your mean approximation, your average approximation is not perfectly accurate. And again, the idea here is to always have this optimal model. Even if something happens, it will give you the slower but accurate model to continue. So this concludes my talk. As I said, the topic was on deriving these virtual twins or hybrid twins, if you prefer, because they are also coupled with monitoring data and using them in a utility-driven fashion, in a utility-driven framework to always obtain at any time the optimal model that can help you for condition monitoring, decision-making, or any application you might have in mind. Thank you. I can stop sharing, I guess, right? And give the floor back to,
Okay, thank you very much. Very interesting presentations. I think we can take some questions from the audience now. If anyone has a question, you could either type it in the chat or just unmute yourself and ask our speakers. While some think of a question, I actually have a quick question. So the predictions, whether from the GNN or the local ROM, were they compared to models that they have been trained on, or were they compared to, let's say, a different data set?
Well, let me first explain that, of course, it depends on the application, but overall, you're right. The process we follow has these surrogate models, these reduced order models that oftentimes are trained. That was the whole point, from the engineering intuition, some full order models. But usually we try to compare them against actual experimental data. This was the point of showing you that example of the blade that was being tested in the lab, where they are compared against the real model. There is no, the real system. There is no actual, virtual model where this validation was conducted. The point was to do it on a real operating system, and that's really the test. Now, not in all cases do we have the luxury to have such data, and that's why in these cases we may have to compare against either an individual simulation from another simulator or a simulator with another mesh, for example, which again would correspond to a different reference model. For the case that was presented by Greg, maybe there I will give him the floor, because what he did was an interesting play with resolutions or different modeling refinements. But again, there, the access to field data is not necessarily so open, which is the major issue we have to deal with. And there we have to do what we can to prove verification, not really validation, which is what comes with real data. So Greg, maybe you want to add to this.
Yeah, and in the course of our work, we had a look at, I briefly explained about this multi-fidelity component, where the idea was to train on very cheap simulations and then to then apply it to much higher resolution simulations with a minimal amount of data. And we saw some success with the transfer, kind of these efficient fine-tuning methods that we applied. But as Eleni is saying, it's very difficult to actually find validation experimental field data from large, wind farms with all the required damage equivalent loads and all the directions. It's very complicated to get this.
The main difficulty is we often, especially for farms, because this is the theme for today's talk, we get access to SCADA information that is almost always available, and some large open data sets exist, but almost never access to information that has to do with structural response from which we can compute the damage equivalent loads. And this is also something we advocate for, the fact that in the standard instrumentation of turbines, we have to start thinking about including also structural monitoring information, which would be something that can be easily integrated in these structures, given that they already have a pre-existing culture of monitoring. SCADA is a pre-existing culture, but it doesn't always include structural monitoring. This is the problem.
I was just wondering if, let's say, the geometry changes or the material properties change, will it still be able to capture the behavior as accurately as it is or not? But I understand the limitations that...
Actually, this was the point of some of the formulations you saw. So what Kostas presented, the premise is that we have to build parameterized reduced order models. So yes, we are trying to make them applicable across parameters that define the geometry and the material properties. This wasn't so necessarily exploited in the case presented by Greg, but it doesn't mean that you couldn't also extend your training sets to include other parameters. One could think of doing this also, yeah.
And in terms of the geometry there, the GNNs are really perfectly suited for this kind. We trained on thousands of different layouts and can apply to any layout, be it 2 turbines or 100. That's really the
I think the geometry
in
question here was maybe you have another wind turbine tower, a different height, and so forth. But then this again, you could imagine.
We tried this with the multi-fidelity component because the Hawk 2 farm data was of a different turbine than on the pre-training set. So.
Yeah. And it's quite an interesting figure you showed, Kostas, with the interpolation of the data. And I was thinking, can you actually extrapolate, or is there any constraints on that or limitations?
Well, this is the idea. This is why we do not apply naive parameter interpolation on the parameter space. And this is why you employ physics-guided or physics-aware schemes. As long as you have enough of the physics instilled in your model, you can get this extrapolation ability. This is not generic, of course, you cannot.
Perhaps one of your plots was for extrapolated parameters outside of your grid. And maybe it wasn't clear, but it was already extrapolation what was shown, not in the plot maybe of the
last one. Maybe, it was the last one.
But the last one was extrapolation. Exactly, because what you ask is the biggest challenge, and this is what we claim, that with physics in the loop, you can tackle this challenge. This is what gives you the strength to extrapolate.
Okay.
And even in that plot, even if you don't get the perfect accurate prediction at all times, you get these error bounds that are close enough to give you a good estimate, even if you're extrapolating a bit far for your knowledge limits. This is the idea.
Okay. Are there any questions from the audience?
Hello, I have a question. Thank you very much for the very interesting presentations. I wanted to ask regarding the last point that Kostas was showing, regarding the balance of accuracy and efficiency through the utility function. So you showed an example with estimating the acceleration, right? Just to understand, is this a model based on physics and data, a regression model where you can set the parameters based on the balance of accuracy and efficiency that you want? How does that exactly work, and how can one determine what is the appropriate balance? I guess it depends very much on the application, but if you could give some more details.
Sure. So the idea is that the user or the operator defines the balance between the attributes. So the operator defines if they need an accurate decision, no matter if it's slow or not, or a very fast one, no matter if it's not that accurate. So the idea is that the operator defines the utility weights, how do these different attributes contribute, how fast or how accurate they want a decision. And then the framework, what it does is that it has all these different, as I said, generic parametric models in its core. It runs all of these in parallel. And essentially, like the filtering paradigm, you compare the response with the data, you have an objective function, and you can get a parameter estimation and a model response estimation as fast as possible. And by evaluating these models, some of them will be fast, some of them will be slow. You, of course, evaluate with respect to accelerations in a redundant sensor. So you use a few sensors for the parameter estimation and the model updating task, and a redundant sensor for the utility computation. Using the redundant sensor acceleration, as I showed, you can evaluate how accurate you are. And of course, efficiency is something that you can count in terms of flops, in terms of seconds, in terms of a number of operations, whatever you want, and you give, yes.
Yeah, I was just going to say that the thought behind this was to give the user the chance to decide what it is they define as adequate. Because it's oftentimes we realize, I mean, all of these models we show have to work with data, usually sometimes in real time. We know that they are approximations, but the users have different desires with respect to what they can tolerate in terms of precision approximation and the time they want to wait for the simulation. So realizing that this is not an absolute, I mean, absolutely given, this utility perspective tries to offer the user the best fitted model depending on their desire at the current point in time. Because maybe you want to run Monte Carlo simulations and you want something that's very, very fast. You don't want to wait for days for a single simulation. In that case, perhaps your preference is to use that model that is fast enough, but still gives you some accuracy you can accept. And this is the point of this analysis from a pool of various models that could be used.
Mm-hmm. Okay, thank you very much.
Let's see if there are any questions. Maybe I can add a quick one. So I'm in structural engineering, so I rarely deal with or attend a presentation on structural health monitoring. But I was wondering if, let's say, you have a limited physical data, and you supplement that with machine learning or GNNs or whatever, how do you avoid overfitting actually? If let's say you have a wind turbine and you have limited sensors and you have just few data, how do you tackle this actually?
Well, again, the physics is the main means to avoid overfitting, because we do not just learn from the data. Even if your knowledge of the physics is partial and limited, I didn't include it in the examples, but we show through various examples that even using a linearized physics in a problem that is nonlinear, you still sort of bias it to offer you a prediction in the physical degrees of freedom, which is really what we care about in structural monitoring, which means that you're not overfitting because there's the underlying coupling that is offered by that physics intuition. So you're sort of drawing the regression away from overfitting by asking it to accommodate the physics equations. This is in fact, inclusion of physics is a way to avoid overfitting.
Overfitting, yes. Okay, brilliant. Well, if there's no more question, I thank our speakers. Thank you very much for the very nice and interesting presentations. And I hope you have a very good day. Thank you.
Thank you for organizing and hosting it.
Likewise.
Thank
you for hearing us.
Thank you.
Bye.
Bye.
Bye-bye.
Thank you.
Thank you. By an introduction, yes.